Within this glass is an invisible contradiction, a yellowish-green mist that once drifted across muddy battlefields now sits quietly in our reservoirs to protect billions. For most of human history, drinking water was a gamble. Before modern chemistry, collecting water meant risking exposure to microscopic pathogens that caused cholera, typhoid fever, and dysentery. Historically, facilities like this hospital ward were overwhelmed with the victims of contaminated water, claiming millions of lives. This constant threat remained an inevitable part of human existence until a specific chemical intervention transformed the landscape of human survival. That intervention comes from the 17th element on the periodic table, chlorine. At room temperature, it exists as a pungent yellowish-green gas, sitting within the highly reactive halogen family. Swedish chemist Carl Wilhelm Scheele first observed the gas in 1774, though it took British scientist Sir Humphrey Davy another 3 decades to identify it as a distinct chemical element. This is a chlorine atom. Its umber ring holds 7 electrons, leaving an empty slot requiring an 8th for stability. Because of this, it reacts aggressively with metals and organic compounds, ripping electrons away to fill that gap. Once it captures that missing electron, it becomes a stable chloride ion. This carved salt mine illustrates how abundant these stable ions are in nature. These deposits form the massive amounts of table salt we consume every single day. This constant atomic pursuit of a single electron provides the mechanism for its extreme reactivity, fueling its capacity to both sanitize water and react violently with organic tissue. In the late 19th century, scientists realized they could turn that aggressive reactivity against disease. They found that controlled amounts of chlorine would steal electrons from the cellular walls of microorganisms, destroying them. Soon, cities began constructing industrial filtration tanks to treat municipal water supplies, neutralizing pathogens before they could reach domestic taps. The outcome was immediate. During the 20th century, outbreaks of waterborne diseases in developed nations plummeted to near zero. This same chemical process is what allows millions to use public swimming pools every day without the risk of transmitting illness through the water. By removing pathogens at a municipal scale, the practice effectively decoupled the growth of modern cities from the threat of waterborne epidemics. Beyond its role in sanitation, chlorine has become a primary component in global manufacturing. It is essential for producing life-saving pharmaceuticals, medical disinfectants, and the millions of tons of polyvinyl chloride, or PVC, used in modern infrastructure. Modern daily convenience relies on chlorine chemistry at almost every stage of industrial production. However, that same chemical reactivity can be turned against human life. In April 1915, during the Second Battle of Ypres, a thick cloud of chlorine gas was released across the battlefield. The gas caused immediate panic and severe respiratory injury. Soldiers relied on crude, early masks for protection as dense clouds settled into the trenches. The biological impact was horrific. The same electron-stealing mechanism that destroys bacteria in a water tank was now forcefully breaking down the organic tissue of human lungs. This deployment marked a turning point in modern warfare, leading to international agreements that eventually restricted the use of chemical weapons. Element 17 is a neutral force of nature, reacting exactly as its atomic structure dictates. Its final impact is determined entirely by how we choose to use it. To maintain our modern infrastructure, we must safely extract tens of millions of tons of this volatile gas every year to meet global demand. This is achieved through the chloralkali process. It begins in an industrial tank filled with concentrated salt water, or brine, containing 2 submerged electrical nodes. As a powerful current passes through the brine, it forces a chemical reaction, separating the atoms of the salt and water molecules. This reaction produces 3 distinct industrial materials: hydrogen gas, caustic soda, and pure chlorine gas. Modern production facilities utilize advanced leak detection and ventilation systems to ensure that this massive volume of chlorine remains contained and under control. Our current standard of living exists because we have learned to engineer strict boundaries around this volatile element. The same gas that weaponized the battlefield now serves as the invisible framework for our hospitals, sanitation systems, and modern medicine. Chlorine is only one chapter in the story of the periodic table. Next is element 18, argon, an invisible gas that shields modern technology and hides secrets behind a mask of total stability. To see how these elements build our world, subscribe to Atomic 118 and join us for the next discovery.